Welcome back. We're talking about mirror descent, and in particular, mirror descent in non-Euclidean geometries. And in this lecture, we're finally going to get into it and give the statement of the result and also the full proof. So to refresh, mirror descent tells us that xt plus 1 is equal to the argmin over x in our constraint set of a linear approximation to f, eta times gt transpose x, plus something that keeps us close to the previous iterate, xt. And this is the whole key to the story. Remember that if we were to replace this with something like 1/2 times x minus xt Euclidean norm squared, this recovers our standard subgradient descent. Projected subgradient descent. So the whole idea is that we're changing d phi. And what this is going to allow us to do is change the key definitions of the constants in the statement of the proof. So as we talked about in previous lectures, the key constants in the rate of convergence are things that govern and control properties of the function, in particular Lipschitz, the Lipschitz constant. So in the next couple slides, we're going to back up just a bit and show that once we change how we measure distance, in particular once we use Bregman divergence instead of just the Euclidean norm, we are also going to change how we measure how Lipschitz a function is, and also how smooth it is and how strongly convex. Everything has to be done with respect to the right norm. So in the next few slides, we're going to talk about what it means to be Lipschitz with respect to an arbitrary norm, what it means to be smooth, and what it means to be strongly convex. Again, not with respect to the Euclidean norm, but an arbitrary norm. So let's move to that. So our definition of Lipschitz, remember, if f is a function from Rn to R, we say that f is Lipschitz with constant L if the absolute value of f of x minus f of y is upper bounded by L times x minus y. Okay, so this is what it means, and everything that we've used so far has had a 2 norm here, but now I'm allowing this to be an arbitrary norm. Now, sometimes I've been using a slightly different definition, in particular in the setting where I want to talk about the gradients or subgradients of f. But I want to link this to something that we had already done before. So note that just by convexity, if f is convex, then note what we have. We have that f of y is greater than or equal to f of x minus plus subgradient, or I might as well just write the gradient here, of f of x times y minus x, or in other words, f of x minus f of y is less than or equal to the gradient of f of x times x minus y, because I moved it over to the other side, so I inserted a minus sign. And we know that this is less than or equal to gradient of f of x, norm of that, times the norm of x minus y. If I were to put a 2 norm here, this would be our usual Cauchy-Schwarz. We discussed this last time. But instead, I can measure x minus y in any norm and the gradient of gradient of f of x in the dual norm of whatever norm I choose. So this means that, looking at this putting absolute values on both sides, I have f of x minus f of y is upper bounded by the gradient of f of x, the dual norm of that, times the norm of x minus y. Therefore, an equivalent definition to saying that f is L Lipschitz with respect to an arbitrary norm is saying that its gradient, or alternatively its subgradient, is uniformly bounded in the dual norm by L. So another definition that we've used f is L Lipschitz with respect to a particular norm is equivalent to writing that its gradient or its subgradients in the dual norm is upper bounded by L. So again, I just want to belabor this point. Note that gradients and subgradients are always measured with respect to the dual norm. And one way to see why this is true is that gradients and the points are always coupled with this dot product, with the inner product. And so if we look here, we see this all the time. And whenever we have this kind of bound, we need to have the dual norm on the gradients or subgradients, and then in order to have the norm on x minus y. Okay, so now we know what it means to be Lipschitz with respect to an arbitrary norm. Now we're not actually going to need smoothness for our proof of mirror descent, but while we're in this flow, it makes sense to talk about smoothness here. So recall our original definition. F is called beta smooth. This is a statement about how smooth the gradients are. So F is beta smooth with respect to a particular norm if the gradients are Lipschitz. So gradient of f of x minus gradient of f of y is less than or equal to beta times x minus y. Now note I left a space here on purpose. I want you to think about what should go here, what norm should this be. Remember that whenever we see gradients or subgradients, we're always going to measure the norm using the dual norm. Now in the past, when we were just using Euclidean norm, we didn't have to discuss this because as we derived in the previous lecture, the 2 norm is what's called self-dual. So in other words, writing a 2 or writing the dual of the 2 norm would be exactly the same thing. But in this case, because this norm on the right, because this is arbitrary, this is an arbitrary norm, I have to make sure that I'm careful and I keep track of what's the dual norm and what is the usual norm. Okay, so this is very similar semantically to the definition that we had before. And if you recall, one of the consequences of this definition that was really important, that basically went into our proof of rate of convergence for smooth functions, gradient descent on smooth functions, what we obtained was that if a function is smooth, we get this quadratic upper bound. In other words, the inequality of convexity is reversed, and I have an additional quadratic. So something similar holds here, we can show, except that I'm going to replace the 2 norm with this norm. So let's derive this carefully. It also is an opportunity to remind ourselves of the fundamental theorem of calculus and to see how it's used. This is a really common technique in convex analysis and convex optimization, so it's useful to have one more trick up your sleeve. So recall that for our L2 definition of smoothness, we showed, I'm just writing out what I said now, we showed a quadratic upper bound. So that means that f of y is not greater than, as is the usual inequality in convexity, but is less than or equal to f of x plus the gradient of f of x transpose y minus x plus beta over 2 times x minus y, 2 norm squared. Okay, so what this basically says, we've seen this picture before, but it's so fundamental that it's useful to have in mind. This is basically saying that at any point of a smooth function, I can fit a quadratic. And remember that we had said that if you take something that's not smooth, say the absolute value function, you can fit a quadratic on top of it at any point except for the origin, except where it has that v. So if you try to do that, you'll see that no matter how steep you make your quadratic, you're not going to, it will at some point dip below the curve, so that doesn't hold. So intuitively, this is what smooth means. Okay, so now I'd like to, I want to show that something similar holds, but with an arbitrary norm. So I want to show that for our general norm or arbitrary norm definition of smoothness, something similar holds. This is a good opportunity for you to go back to the lecture where we showed that smoothness implies this quadratic upper bound and ask yourself, were there any of the techniques that we used there that inherently relied on Euclidean geometry? And you'll see that the answer is yes, that we used some steps that relied on Euclidean geometry. So we're going to give a more general proof that doesn't require that, and it's going to allow us to use this, to treat this case. And the key tool that we're going to use is our old friend, the fundamental theorem of calculus. So what does this say? It says something really simple. Basically that the integral is the inverse of the derivative. So if I integrate the derivative, the integral of the derivative is just the function evaluated at the endpoints. So let me just write it like this way. The integral from 0 to 1 of d dt of some function f of t dt is just capital F, my function evaluated at the endpoints. F of 1 minus f of 0. Okay, simple enough. We're going to see how we're going to use this. So what is it that I want to bound for my quadratic upper bound? I want to control f of y. I want to show that this is upper bounded. Let's write up here what we have. We want to show that f of y is upper bounded by f of x plus the gradient of f of x times y minus x plus beta over 2 times x minus y squared, but not subscript 2. So this is not the Euclidean norm. Okay, so this is what we would like. So let's see how we can go about this. So the absolute value of f of x minus f of y minus gradient of f of y transpose x minus y. You know what I've done here? I've switched my x's and my y's. So let's, so as to not confuse you here, let's rewrite this in exactly the notation that we're going to have. I'm going to show that f of x is greater than f of y plus gradient of f of y times x minus y plus beta over 2 x minus y squared, just to be consistent with what I'm writing here. So what I've done here is I've put f of y plus gradient of f of y x minus y over on the left-hand side, and I'm subtracting it from f of x. So I'd like to show that that this is a quadratic upper bound, that this is upper bounded by something that looks like this term on the right. This is eventually where we're going. Okay, so now the key trick here that comes from fundamental theorem of calculus. Note that this thing that I've written, this is just equal to. This is just equal to, by the fundamental theorem of calculus, the absolute value of, I'm going to write this as an integral of a derivative. The integral from 0 to 1 of d dt times f of y plus t times x minus y, close parentheses, that's the end of taking the derivative, minus the gradient of f of y times x minus y. All of this dt. Okay, so have a look at this and see why is this the case. This right-hand side here, this last little bit here that I'm pointing to here, this is just this portion here of my expression on the left. So let's look at what's under the integral. So by the fundamental theorem of calculus, this bit here is the integral of the derivative is just what's the function evaluated at the two endpoints, t equals 1 and t equals 0. So if I plug in t equals 1, what do I get? F of y plus x minus y, so f of x. So this is exactly f of x minus this thing evaluated at t equals 0, which is just f of y. So indeed, I have f of x minus f of y minus this gradient. Okay, so the left-hand side is indeed equal to the right. Okay, let's clean this up a little bit and then keep going. So looking over, let's actually compute this derivative. To compute this derivative, I need to use my chain rule. It's pretty simple what's going to happen. So this is equal to the integral from 0 to 1. What's the derivative of f of y plus t of x minus y? It's just the gradient of f of y plus t times x minus y. That's the first part. That's the first part of the chain rule. And then I need to multiply by the derivative of the inside. Again, I'm taking a derivative with respect to t. So you should think about this as just a single variable function, just a function of t. What's the derivative of the inside? X minus y. X minus y. And then what I had over there on the far right. So minus the gradient of f of y transpose x minus y dt. Okay, now I'm going to group these together. So this is, again, equal to the integral from 0 to 1 of the gradient of f of y plus t x minus y minus gradient of f of y. All of this transpose x minus y. So perhaps you can see where this is going. Remember this, what is this? This is just u transpose v, our old friend the dot product. And when we have a dot product, we can upper bound it using, again, we're not going to use Cauchy-Schwarz. Cauchy-Schwarz would tell us that this is the 2 norm of u, upper bounded by the 2 norm of u and the 2 norm of v, but we don't want that. We're going to use what's called Hölder's inequality. And Hölder's inequality is going to give me the exact same thing, except I can use any norm and its dual. So it's the norm of u dual times the norm of v. Okay, so we're going to use this because I have this dot product right up above. So this is then less than or equal to. I can now drop the absolute value because the norms are just going to be positive. So this is the integral, less than or equal to the integral from 0 to 1 of the 2 norm gradient of f of y plus t x minus y minus the gradient of f of y. This is the dual norm times the norm of x minus y dt. Now, why is this good news for us? We finally brought it into a form where we can use our main assumption. So let me just flip back here for a second so you can remember what that is. What are we doing here? We're talking about smoothness. And smoothness tells me that the norm of the difference of the gradients is upper bounded by a norm of x minus y. And that's exactly what I have. So let's go back and see how this fits. You see here, I have the norm of f evaluated, I have the gradient of f evaluated somewhere minus the gradient of f evaluated somewhere else. So this is upper bounded by the integral from 0 to 1 by beta times the difference here. That's exactly what the gradient being Lipschitz means. What's the difference here? The difference is of the arguments. Here I have y and t times x minus y, and here I have y. So the difference is just t times x minus y. And the norm of that is t times the norm of x minus y, not the 2 norm, not the dual norm. This is our arbitrary norm. And then I have my x minus y dt. This is equal to, I'm going to take outside of the integral everything that doesn't depend on t. So this is equal to beta times x minus y, arbitrary norm, but now squared, times the integral of 0, 1, t dt. This is finally something that we know how to do. This is just t squared over 2 evaluated at 1 minus t squared over 2 evaluated at 0. In other words, just 1/2. So this is equal to beta over 2 x minus y squared. This is exactly what we wanted to show. So put these two together. This is upper bounded by this, and that inequality exactly implies this inequality up top that we wanted to show. So that's smoothness. We've shown that if the gradient is Lipschitz, then we have this quadratic upper bound, and that this holds it with respect to an arbitrary norm. We don't have to work quite as hard for strong convexity. The definition is straightforward in this case. So remember that strong convexity is a quadratic lower bound. So F is alpha strongly convex with respect to a particular norm if f of y is now greater than or equal to, so lower bound, f of x plus g transpose x minus y, y minus x. Again, g is just any element of the subdifferential of f at x, plus alpha over 2 times x minus y, arbitrary norm squared. So this is what we're going to use. So we're going to use these properties. In particular, we're going to use strong convexity, and we're going to use Lipschitzness in order to give the statement and then the proof of mere descent. So we're going to stop here and pick this up in the next lecture.